Guys, so this is another emerald out. So here a long piece of paper is being pulled on a horizontal surface with a constant velocity u. So this is how it is being pulled. This is the paper. Width of the paper is given as L. A small block moving horizontally perpendicular to the direction of the motion of the paper. So this is all the top view with velocity v. So this is this guy slides onto the paper. The coefficient of friction between the block and the paper is mu. Find maximum value of v such that the block does not cross the opposite side of the paper. Yeah, so maximum value of v, very high v it is going to cross, so there has to be a certain v till which it just stops on the other side. So what kind of motion is going to be on the paper? So as soon as it gets on the paper, with respect to the paper, what is the motion felt? Say something is stationary and you put it on a paper which is itself moving with a certain velocity u. So with respect to the paper, what happens? This was stationary with respect to ground, so it will try to remain at its own position, but somebody on the paper is going to see it going back with you. And this guy was obviously having a velocity v in that direction. So since the paper is going with a constant u, this guy will achieve a constant velocity. Friction will act and reduce the velocity, but as soon as it gets on it, it will have a velocity of v square plus u square under root in that particular angle. So while it is on the paper, is the angle going to change? No, the angle is not going to change. It is not going to have a curve or something. Why? Because this paper is not accelerating. As soon as you are on a paper which is moving with a constant velocity, if it is moving with constant velocity, there is no force or pseudo force acting on the body which is on the paper. It is as good as a constant velocity is as good as thing not moving. So with respect to the paper, if we think, then the paper is not moving and the body initially attained this velocity v square plus u square under root. So this question becomes as simple as, on the paper somebody has thrown a body with this v dash velocity which is v square plus u square under root. What is going to happen? So it is going to slow down. The friction is going to act exactly in this direction, right? How much length it is going to travel? So this angle is known. Why this angle known? Because the v and u is given, so that angle is known. So the angle theta, the sine theta, is going to be given by this v upon v square plus u square. The total length it is going to travel is L by sine theta, and ultimately here when it reaches over here with respect to the paper, so its velocity is going to become 0. Ultimate velocity is going to become 0. So if we apply v square is equal to u square plus 2s, then the final velocity is 0. Initial velocity is v square plus u square, by the way. So this is your initial velocity, this is your u dash square, where v dash square has become 0 is equal to u dash square plus 2as. So here the 2as is, the acceleration is negative because the friction is in the opposite direction. So v square is equal to u square plus 2s, where the final is 0. If you apply, we get this equation. They have asked what is the v in terms of mu and all is given to you. So what is the acceleration? Acceleration is friction divided by the mass. So friction is mu mg. This is the top view. This weight mg. Downwards, normal reaction is mg upwards, so the friction is mu mg. So the acceleration is mu g, and the length it has to travel is L by sine theta. So if we solve it, we should get the answer. Let us see how easy the solution. Putting sine theta as v upon under root of v square plus u square. you land up with this. Now you need to square this. If you square this equation, you get this one, u power 4 v power 4 plus 2 u square v square, and the other side a square of this, a square of this, a square of this, a square of this v square plus u square upon v square. So it is looking little troublesome, because if v square is taken on the other side, we'll have a v power 4 over here happening. We have a v power 6 over here happening, and we are still having a v square over here. So there are three terms of v power 4, v power 2, v power 6. So it is a cubic equation of v square. So taking yeah, it's a cubic equation of v square. You have a u square term, so there's a constant also, you can't cancel, and you have to solve it. So we can approach a little differently. The other approach would be, we'll just take the vertical component. So vertical component was v. So the friction which is acting this way has got a downward component. So the downward component of the friction will be your mu mg sine theta. My theta is this. So my theta is this. So this is my mu mg. This is my mu mg sine theta is my component which is reducing my v. So the deceleration on the velocity v is mu g sine theta. So if I write that v ultimately becoming 0, so if I apply a v square is equal to u square plus 2s, this initial v is your v square is the 2a, and this time the s length is l across. Again we'll put our sine theta is equal to v upon v square plus u square under root and try to solve this. So when we do this, we see that we are getting a v power 4 and v square, so which is in a quadratic format, not a cubic format, so easy to solve. So this is what you get your solution as. Few fine things what you can appreciate or note down is, see, this is the mat, the paper. Is my angle going to change anytime? If the angle is going to change, then I can't have a constant deceleration of mu g sine theta. It is not going to change because it's simply a case of a body on a paper, a body thrown in this direction. So the friction is exactly opposite to this. Why will it change? The other thing what you can consider is that if I apply in this direction a f component backwards, then, or shall I put it this way? I'll put it this way. Is my v reducing at the same, reducing at a rate which is proportional to with which your u is reducing, so that the angle is maintained the same? So you can cross check that. Okay, so what happens to v? V becomes a v dash is equal to v minus f y, may I call it. So this is your f, this is your fy, fy by mt, and u dash is u minus fx by mt. So a good thing for you to see whether they are reducing in the same proportion or not. Are they stopping at the same time or not? So it is, all of it is right. When v becomes 0, at the same moment u will become 0. So you can cross check with the friction components. U becomes 0. because after all it has to maintain the angle, and that is the time the whole velocity also becomes zero. So that's the time this also becomes zero. So this equation should hold good. Once you have got this equation, you can, it would be a little trouble, but yeah, you can verify that this equation is also giving the same thing. So you have to double sure in your mind that it goes in a straight line, and once you are convinced, the question is easy to be solved.